Hello, and welcome to the fourth lecture from Chapter 5, from Cosmic Perspectives, ninth edition. This chapter is all about light, and in the previous three videos covering sections 1, 2, and 3, we discussed where light comes from, how it interacts with the world around us, and we started discussing matter. Well, we're going to bring some of those discussions together in this lecture covering section 5.4, the fourth and final section of the chapter. We're going to talk about how light interacts with matter, which we started to when we discussed the energy levels of the electron, all those points where an electron can go that are not full ionization, but just excitation, and how that involves the absorption and release of photons. But if that idea was a little confusing and abstract, we're going to make it more clear in this lecture because we'll see exactly what it does and how it's used by scientists, by astronomers, okay? So we'll lay some groundwork and tie all these things together, and let's look at the questions that we're going to be answering. One of those is, what are the three basic types of spectra? Next, how does light tell us what things are made of? See, that's an important one. That's going to get to those energy levels inside the electron. Next, how does light tell us the temperature of planets and stars? This is another amazing thing that light can do, totally separate from the electron excitation levels. Maybe, based on the same physics, sure, but very different phenomenon. And finally, how does light tell us the speed of a distant object? So impressive here, right? That after explaining a little bit of background about light, we can hopefully make sense of the amazing utility. Because, light can tell us speed, temperature, and composition. That's amazing, right? We don't have to take the object and put it in a device. You don't have to spin it and separate it. There's no necessity of a sample. Just by looking at something, you can determine its speed, temperature, and composition. And it's not easy, and it's difficult to do, and sometimes things will interfere with the measurement, but the very idea that it's possible is amazing. Okay, so what are the three basic types of spectra? Well, the word spectra, first of all, refers to some sorting of light by wavelength or frequency and so on. It's the same term that we used when we talked about the entire electromagnetic spectrum. There is a singular spectrum because there's only one electromagnetic spectrum, because it is the entirety, all the way from the longest wavelengths to the shortest, and the highest frequency to the lowest frequency, right? That is in its entirety, but we can look at smaller pieces of light, smaller distributions of light, and we still call those spectra. And maybe these are spectra that come from a source that creates a rainbow, like the sun, or maybe these are spectra that come with just a few spikes of color, like from a neon sign. And those are going to be the different types that we want to make clear. Okay, and the names are, and they make sense. I think they're very evocative of what the spectra represent. Continuous, emission, and absorption. Okay, those are the three types. All right, why are there three types? What makes the three types? We're going to see. Okay, now in reality, it's important to acknowledge, and I think it's a good way to learn this, that when you look at some signal, like the light reflected off a planet, or the light emitted by a planet in the infrared, or when you look, of course, at the light from a single star, or from a nebula, or a galaxy, whatever it is you are looking at, a radio galaxy with a radio telescope, okay? There's usually not going to be just one type of signal. There's going to be combinations of signals, light signals, and those light signals will take the forms of the three different spectra. In fact, this figure right up here includes all three of the types of spectra: continuous, emission, and absorption, okay? And down at the bottom, we can see that this, graph on the horizontal axis is showing us wavelength, okay, from the shortest wavelength with ultraviolet up to the longest wavelength with infrared. Visible light would be sandwiched between those two, ultraviolet and infrared. This isn't showing anything beyond ultraviolet and infrared, so no microwaves, no X-rays, okay? So it's visible light plus a little bit on either side, okay? On the vertical axis is intensity, which is just how bright something is, how much power per area we would get. In other words, how much that particular signal dominates. So at quick glance, we can see that there's a lot of color somewhere between green and red because there's a big spike right there. And there's also a spike in the longer wavelength, somewhere in the middle of infrared. And beyond that, we can see there's little spikes, not mountains, but just weird little jutting spikes over in the ultraviolet. And it looks like someone took a bite out of the infrared hill, and it's the opposite of spikes. Okay? So those features are what we're going to discuss. Each of them, whether it's the smooth hill or the smooth mountain or the bites or the little spikes, each of one of those will represent one of the three. Okay? Maybe you can even guess which one are which. Okay? So the three types of spectra can be understood if we think about a source and an observer. Okay? So imagine that you have some way to catch the light, like a prism, and you're observing this is more like a screen, and you're observing the light, right? And you, the scientist, or a computer is making a measurement. Now, before the light got to that screen or that measurement point, the light was produced by a hot light source and then shown through a prism to split the colors. The result is a continuous spectra shown here on a graph of intensity as a function of wavelength. And the reason it's a continuous spectra is because it's a smooth curve. It's producing a lot of colors. There is one peak wavelength, but it just falls off to either side. It's not a spike, okay? It's not just a one signal, it's a curve of signals. Notice the type of source, it has to be a hot light source. The term for this is a black body, and basically it's everything that is not a gas. Any object that's solid, even a star, you might say, well, aren't stars technically gases? But they're under such heavy pressure, they're behaving much more like a liquid or a solid. And really, any planet, any star, any person, or any object on the surface of Earth are going to be considered a black body. The only things that aren't are an excited gas, a very low density material. And all black bodies emit radiation. They emit light in the form of lots and lots of different vibrations. It's almost like you had an electron that had an infinite number of different energy levels rather than just a few predefined energy levels, as we saw in the previous lecture, and that would create a continuous effect. So the light is still being produced in fundamentally the same way, but through a whole series of different vibrations at the molecular level, okay? And so the fact that the material, like the metal used in a light bulb, is not just one pure element, and it's not able to behave exactly in the uniform way of every element having the same energy excitation levels, because it's so many different elements and so much different possibilities of behavior, different ways things can move, that results in so many different types of light, okay? And it turns out that the only real information that can be gained from this type of spectra is temperature. It's directly tied in with temperature, but this type of spectra will tell us nothing about composition. So bummer on the one hand, it gives us no information about composition, but is it amazing that it has a direct tie-in with temperature? So it has its own story to tell. Now, the other types of spectra do tell us composition. So the last two, which are very related to each other, the only other two, emission and absorption, they do tell us composition. Emission is where you have a cloud of hot gas, hot enough that the atoms inside of that gas have electrons that are regularly absorbing energy, probably through collisions, right? So there's a kinetic energy getting converted to this potential energy of the electron. And then when the electron relaxes from a higher potential energy state down to a lower potential energy state that falls inwards towards the nucleus, well, it's not going to go back to producing kinetic energy, the thing that stimulated the electron excitation in the first place. Instead, it's going to emit pure radiative energy as a photon. Now that photon might, bump into another atom, but eventually some of those photons escape the gas, this gas with lots of little collisions, a warm or hot gas, and that light just continues on its way out into space. Now that light carries with it an exact story of the atoms, because all those unique levels of electron excitation all correspond to unique frequencies and unique wavelengths of light, which will exactly show up when we split the light in a prism, just like we did with the continuous spectrum. But we don't get that curve anymore. We don't get a rainbow. Instead, we get mostly darkness, with just a few well-defined colors. So this is visibly what it looked like on a screen if we were to develop the colors, or even if you look at with special goggles or something, special glasses, or sometimes it's simple, right? You can kind of see the prism effect as it spreads out through the air, right? Reflecting off of dust particles in the air. But whatever method you see this, you can quite literally see this in a physics lab or astronomy lab. Okay, and the effect tells us the composition. And if there was more than one type of atom in the cloud, it might be a more complicated spectra with lots of lines, but the composition could still be determined with significant computation of splitting them apart and being able to tell which element is which. All right. Usually computers are going to do the really hard part of taking complex spectra. All right. But some of them are literally just a single atom that's in the cloud, especially hydrogen, being by far the most common element in the universe. So we can really clearly tell that this cloud is all atomic hydrogen. And astronomers can then make measurements of density and so on, and the mass of the cloud, and look at its dynamic behavior, all because we knew its composition in the first place. Now we can also gain information about composition, so the exact same information, but instead of having a cloud of gas that's sufficiently hot or sufficiently bright compared to its surroundings to send a clear light signal to us, instead we can have a cloud of gas that's positioned right in front of a black body, a type of light source that would create a continuous spectra. In this case, a light bulb, but could just as well be a star. Both clearly, are classified as black bodies or, this type of continuous spectra producers. All right. So that rainbow, that full continuous spectra, then passes through the cloud of gas. That cloud of gas is going to absorb those photons that exactly match the possible energy transitions of the electron from one of those predefined, quote unquote, orbits to another. And there's many possible, steps that the electron can take, right? Even taking steps from a higher level to a yet higher level, say from level 2 to 4 or 4 to 7 or something, right? Those are less probable, but they do happen. Point being is that what's going to be happening is all the possible wavelengths of light, because after all, it's a continuous spectra, is as they shine through the cloud, well, some of them will happen to match, right? And so those are the ones that get absorbed by the cloud. Now, the cloud doesn't hold on to them forever, right? The cloud is also going to be eventually letting the electrons relax and just emitting the exact same photon that it absorbed in the first place, basically acting like a transparent material. But interestingly, we don't see the emission because in this case, the star or hot light source is so much brighter, has so much more intensity, that really the only signal that a ground-based or near Earth-based human telescope can pick up looks different than the emission spectra. It looks like what's called an absorption spectra, which is just the gaps in the rainbow. But here the gaps in the rainbow represent the element of the cloud that was between us and the rainbow source. Okay? Tells us the same information. As I said, the same amount of composition, tells us the exact element or elements that are in that cloud. Okay? But by the way, it doesn't tell us anything about the temperature of the cloud. Okay. Right? So these are just summarizing each of them. As I've gone into so much detail on the lead slide, we'll just quickly go through these. These are good for your own reference. So we have the continuous spectra, right? One source or one word that gets used a lot for continuous spectra are incandescent, right? So anything that glows hot is incandescent. It's just another term for a continuous spectra source. All right, here was the emission line talking about a low density cloud, right? But that's bright enough compared to its surroundings or hot enough to send the light all the way to Earth. And then another common situation, having a cloud between us and the hot source. And this is, when you see this, you might think, oh, there's a hot source, maybe it's a few light years away from the cloud, but they can actually be very close to each other. In fact, they can be right on top of each other. So one of the big things that astronomers do when they look at stars is they look at absorption spectra, because the elements that exist in the star also exist in the atmosphere of the star, because stars are so tumultuous. The heavier elements aren't really able to sink down. They're kind of mixed up throughout the composition. And even if they're not in the atmosphere of the star, because stars do have atmospheres of many types, they may just be within the star itself, and photons that were making their way to the surface of the star produced inside the fusion core, well, some of them bumped into just the right elements, got absorbed, and the re-emission was just too weak to get picked up by us as a signal. Point being, essentially the star is acting as its own cloud. And when we look at an absorption spectra, we see the elements that exist in the star, especially the heavier elements, those that are not involved in the fusion, the power output of the star, but just these things that exist because the star itself was built on the remnants of previously exploded stars that produced the heavier elements like gold and uranium and all those things in the first place, or even less heavy things, carbon, beryllium or something, right? And here it is. This is, as we started the very first video, the first section of this chapter, this is a continuous spectra from our sun. That's great because the brightest color would tell us the temperature, okay? But what's neat about continuous spectra from stars is they simultaneously are absorption spectra, so we can see important elements that exist in our sun, right, that got absorbed by photons on their way out of the star, right, our local sun. So 2 bits of information on this one, since it's serving as both a continuous spectra and an absorption. Okay, so this is just reiterating the idea that I kept going back to, the tie-in between section 3 and section 4. Each type of atom has a unique set of energy levels. So those are those electron excitation levels, okay? Whatever one we show, it's going to be unique to that atom. Each transition corresponds to unique photon energy, frequency, and wavelength. Remember the ideas, E equals HF. E is the energy between 2 levels of the electron. E is also the energy of a single photon, energy of both, they match. Meanwhile, F is related to lambda through the speed of light. Constants, H and C, never change, okay? So there are downward transitions that produce light. These are the emission spectra. This is an electron relaxing and producing particular energies that correspond to particular colors. Here are some real examples for hydrogen. With a 656.3 nanometer line, that's red light, and then the shorter wavelength, higher energy 486.1 nanometer line, which is a sort of bluish light. We can then see the counterpoint, the same exact information, the same element, still hydrogen, but now between us and a continuous spectra, an incandescent source, and we see the absorption lines telling us it's hydrogen, okay? But hydrogen isn't the only element out there, right? It's such an important one, really. I mean, the universe did start as almost 80% hydrogen, but the next most common, next most important is helium, and in all the processes of the universe since the Big Bang, many other heavier elements have been produced, all inside of the cores of stars. Well, some of the heaviest actually produced by supernovas themselves, but that's a story for another day. But we have things like sodium, neon, all that produce their own spectra. And spectra vary dramatically. I mean, we see sodium has very few lines in the visible range. It would have more lines probably certainly in the ultraviolet. But the neon just has a huge cluster of lines. So there's a lot of complicated behavior that sets the particular levels for that element, especially owing to what are the stable isotopes for that element, which create variation. So it's not just a matter of having, an extra proton. There's often a very different atomic mass between side-by-side elements on the periodic table. All right. So here are examples of lines on top of lines. So a more realistic signal that an astronomer would see would have combinations of helium, oxygen, in particular ionized oxygen, shown here by the fact that it's missing an electron and has a net positive charge, and also ionized neon, all right? And so all these things together create a complicated signal, but one that astronomers can parse apart and tell us what's in there, right? Including the hydrogen lines, which are denoted below, all right? So the solar spectra, with all its absorption lines, tells us the elements that exist inside of the sun, as I said, okay? Now, an idea I hinted at that I just want to touch base back on, continue back on, about the justification for continuous spectra. I said that there's all these possible energy levels, not just a few. And so again, let me reiterate with a picture, right? So with pure elemental substances like clouds, right, that are almost all hydrogen or just a few elements, the dominant way of conceptualizing energy, of realizing what's happening with energy is this energy transitions of electrons. So electrons jumping up to a higher level, and then eventually relaxing back down to a lower level, all right? And in that process, picking up a photon here, all right? So a photon of light, which is both a wave and a particle, which did the excitation in the first place, and after the relaxation, producing a photon, another wave particle, sending it off into space, okay? So that is what dominates the behavior. That's what is actually called the quantum behavior. The fact that there's all these well-defined steps, and you can't go in between, right? You can't go halfway in between. Well, that same idea does explain continuous spectra, and the molecules, or even the atoms bound in a solid, can rotate and vibrate in only particular ways. And you can actually show figures with the same sort of energy levels like you would for an electron around a nucleus of an atom. But now the energy doesn't represent an electron in orbit, quote unquote. Instead, it represents a rotating or vibrating, in this case, diatomic molecule. But then there's so many other options that more complicated molecules can do, so many other what are called degrees of freedom, ways they can, gain energy and then release it back. So it's still actually discrete steps, which means it's still, you can't go in between the energy levels. It's still quantized, but just with so many steps that effectively it looks continuous. All right. So the large number of vibrational and rotational energy levels can make the spectra of molecules very complicated. Okay, very, very complicated, essentially making them continuous spectra. But the fair point there actually kind of is an in between, where you can have something that is simple enough that you can kind of tell from some figure like this what it's made out of, but also approaching a continuous spectra. It's a gray area, of course, right? We simplify things as we teach them in an introductory class like this. Okay, right. So let's do some thought questions by looking at this more real life spectra, one of the ones I led with, and talking about, what is what. I hinted at it a bit, but I haven't told you the answers yet. So let's go through and answer a series of questions. Okay, so this just is going to be a check of making sure that we understood the differences between the spectra. So which letters or labels absorption lines? Okay, so which ones are absorption lines? Pause the video if you need to, but make sure you can identify of the options A, B, C, D, or E, which are absorption lines. There could be one or more. Just D, okay? So D are absorption lines. The bite out of the otherwise smooth hill represent absorption lines. Some element was in between us and an incandescent source, and certain particular energy levels were absorbed, telling us what was there. Which letters or labels the peak greatest intensity of infrared light? So you're looking for the peak wavelength, the most common wavelength, the one that you would probably see if you saw the source, if you could see infrared, okay? And which letter labels that? Your options again are A, B, C, D, and E. Pause the video if you need to. It's E, all right? So E has higher intensity, represents the peak of the infrared light. Which letter or letters labels emission lines? Emission lines this time. You recognize them? It's A, right? So just A, great example of emission lines, some hot source, but a hot atomic source, okay? And do you know which one's labeled continuous spectra? Well, that was easy, wasn't it? B and, somewhere between D and E. Should we call it D and a half? Right here, all right? So B, and I guess E was the peak, but both of these are continuous spectra, all right? Even when they kind of have a cliff on one side, still a continuous spectra. There's no huge chops out of it, nothing that would show an absorption line, just some asymmetry in the behavior on one side, of wavelengths versus the other, all right? But these would be two sources of continuous spectra. So some particular objects that are, essentially glowing in this, this color. All right. So how does light tell us the temperature of planets and stars? So far, I told you it does, but I've spent a lot more time justifying how we can know composition from light, right? We talked a lot about energy levels, even molecular energy levels. But how do we know temperature? All right. Well, nearly all large or dense objects emit thermal radiation, including stars, planets, and people, right? And I said those are all solid objects, anything that isn't atomic or relatively simple. An object's thermal radiation spectrum depends on only one property, okay? So bummer, no details about composition, but it tells us temperature, right? Which is so important because then we can relate that to energy and have, direct functional relationships between them, okay? So the idea is this. Hotter objects emit more light at all frequencies per unit area. So hotter things, just more energy, right? More wattage, okay? hotter objects also emit photons with a higher average energy. So there's a direct relationship between the average energy per light particle and the temperature. And it was experimentally determined a couple hundred years ago what the mathematical relationship was, giving us a direct law and a way to relate a continuous curve and its peak wavelength to temperature. For example, if we look at a curve like this red one here that has a peak with a wavelength of something just beyond 10 to the third nanometers, we can tell right away, because of the location of that peak, that it is a temperature object that is 3,000 Kelvin, and it happens to be a star. Okay, such an important way to classify stars. And hotter stars like this 5,800 degree or 5,800 Kelvin, you're not supposed to say degree, or 15,000 Kelvin, right? Stars, so hotter and hotter stars, they have lower and lower wavelength values for their peak because the energy per photon has gone up, which means the frequency of the average light has gone up, which means the wavelength is shorter and shorter. So hotter stars go from being red to being yellowish to being blue, in fact, and even ultraviolet with the hottest stars. So, which is hottest, a blue star, a red star, or a planet that emits only infrared light? Okay, so what was the relationship between temperature and wavelength? Right? I kind of said it, but what is it? A blue star, okay? And as I said, there's even hotter stars out there that are ultraviolet stars. Now, why don't we glow in the dark? Because we made a big deal that all objects, including people, create thermal radiation. So, why don't we just see each other glowing? All right, so look at the best answer here. Yeah, we do glow. We just can't see it, okay? But we do glow. All right, so how do we interpret an actual spectrum? Well, let's get back to this one. We keep kind of coming to it. And maybe you started wondering, does it actually represent something real with these two continuous spectra, one in the visible and one outside the visible? By carefully studying the features in a spectrum, we can learn a great deal about the object that created it. So in this case, let's actually ask ourselves, what is this object that we keep, looking at its spectra? Because it is actually a real object, okay? It is a real celestial body. Let's see what it is. Do you think it's a star? Right? So we see that there's thermal radiation with an infrared spectrum peaking at a wavelength corresponding to a temperature of 225 Kelvin. That might seem like a big number if you're not familiar with Kelvin, but it's time to get familiar with Kelvin. It's common in astronomy, and it's not. So 273 Kelvin is 0 Celsius, which is 32 Fahrenheit. So room temperature is about, just under 300 Kelvin. So this is really cold. This is freezing cold. This is probably as cold as it ever gets on Earth. Okay, and that's where that's what this signal is telling us is the average temperature of whatever is that source. Okay, so that means our object, I guess, is cold, but isn't it also simultaneously hot? I'm confused. Okay, well, it turns out the absorption lines over here are carbon dioxide. Astronomers, scientists easily recognize those. They're famous absorption lines. Now, to be fair, this is a molecule, but it happens to be a molecule that at least has some easily identifiable absorption lines. All right, and then there's also some ultraviolet emission lines. All right, so that's telling us that whatever this source is, it has some really hot region, and that's usually indicative of an atmosphere, even a very weak atmosphere, a thin atmosphere. There's something going on with absorbing X-rays, and then after following that X-ray absorption, some emission of lower wavelength, slightly lower energy light, UV. All right, and that's kind of like our own atmosphere does. It has a very thin, hot, very very hot upper atmosphere that's absorbing X-rays and releasing some UVs. Incidentally, on Earth, many of those UVs then get absorbed themselves by our ozone, and then others obviously are directed away from the planet. But in this case, we're definitely seeing some emission from ultraviolet. Interesting. And then we see a continuous spectra of visible light, which basically would tell us sunlight, right? Except some of the blue is missing. Well, that's interesting. So that tells us something. Because if this was a source, then it really should be a smoother curve. We really should have, because sources of continuous spectra, black body radiation, incandescents, right? People, light bulbs, stars, all those types of sources, not thin gases, right? Well, they really are going to be more symmetric. I before I said, yes, it's a little asymmetric, but there's a reason for that, and it's reflection. Reflection of continuous sources create this type of behavior, create little, lopsided effects. So that means that this isn't actually our sun. This is just an object, or a star that is. This is just an object that reflects sunlight. Oh, like what? Maybe a moon? It's Mars, all right? And it's Mars because the moon would be colder, right? Yeah, on average. And also, we know it's Mars because Mars does have an atmosphere, a thin one, right? Now, no good for breathing, but it does have a thin atmosphere. So that's big in terms of the ultraviolet emission because the absorption of the X-rays up there. And then the CO2, that's what the what all Mars's atmosphere, I'll reiterate, is very, very thin, okay? But it's basically all CO2. So if there's going to be a signal, it's going to be CO2. There's no free oxygen at all in Mars's atmosphere. So how does light tell us about the speed of a distant object? This is our last question, okay? I know it's a lot of ideas here, but this is the last amazing thing that light can do. Well, it's all based on something called the Doppler shift, which you may have heard of in reference of sound, okay? Because the Doppler shift can tell you about the relative motion of distant objects because photons behave as waves, just like sound waves. So they'll follow all the same rules. If an object is moving towards an observer, the observed wavelength of light decreases. The term for that, we call it blue shifted. We call it blue shifted because in the visible spectrum, if something becomes shorter in wavelength, it becomes bluer, hence the term. Now, blue shifted is freely used for any light or anything in the electromagnetic spectrum. So we even could talk about ultraviolet being blue shifted, which would just make it more ultraviolet, or maybe actually push it all the way into X-rays. So, but regardless, it's anything going in the direction of shorter wavelength is called blue shifted, all right? So it's lambda decreasing. On the other hand, if an object is moving away from us, okay, then it's red shifted. That's because its wavelength got longer. Okay, so those are the rules, but do they make sense? Why the heck are wavelengths changing? And this would be for all spectra, by the way, continuous, absorption, and well, emission. All of those would get shifted depending on the relative motion to us, the observer, us on Earth. All right, well, it just all comes down to waves. So the idea works perfectly fine with sound. You can imagine a stationary train that's creating a siren, right? Or, like ringing some sound on top. Well, that sound is going to travel off, hitting two stationary people. Now, see, everything's stationary, and they just both hear the same tone, right? But if the train is moving quickly towards one observer, then it would simultaneously be moving away quickly from another observer. In this case, the two observers don't hear the same pitch sound because the observer behind the train is going to perceive a longer wavelength sound, which is going to make the frequency lower and going to make it have a lower pitch, all right? Sound terms, but they have their equivalence in light. All right. On the other hand, the person in front of the train with the train moving towards them is going to have the sound hit them with a short wavelength, thus a higher frequency, a higher pitch. So this is the blue shifted because higher pitch is the equivalent of becoming more blue when you go from sound to light. And this is the red shifted over here. All right. So the effect, if you've ever had a siren pass you, is the characteristic right? High pitch moving towards you, low pitch moving away, okay? And it works for light as well. Now, we don't perceive it if we just move a light bulb back and forth. The light has to be moving at hundreds of thousands of meters per second, okay? Now, even a tenth of the speed of light in some cases, or even closer, all right? So the idea works something like this. We have some known specimen. So we either know exactly what to expect for the continuous spectra if it was at rest, or we know exactly what to expect for an elemental emission spectra because we measured in the lab at rest. So here is our laboratory spectrum with the locations of a blue, green, and red line. If we have a source that is moving away from us and is red shifted, all the lines get moved towards the red direction. All right. If the object is moving away from us even faster, then the shift is more dramatic, but of course still in the red direction, the longer wavelength direction. All right. Longer wavelength going that way. On the other hand, if the source is moving towards us, then the shift is blue. And if it's moving towards us a lot, then the shift is more blue. All right. So I have, let's see, greatest blue shift. Okay. Wait, where'd that purple line come from? Right, because we have the green line, the yellow. Object 4, greater blue shift, object moving towards us faster than object 3. Yeah, well, I'm trying to follow along with it. Oh, I see, it just shifted into different colors. Duh, right? I'm like, well, this because it became this one, the blue one, shifted so far it became purple. I wasn't paying attention to that with the red because it essentially just all stayed red because it's such a large region of red. But here, this line started off as blue. When it shifted a little bit with the blue shift, it was still a shade of blue. But in the case when the object is moving even faster towards us, the line that was blue gets shifted into purple, right? Well on its way to violet, right? And the red actually became orange with the more extreme blue shift. All right, so we generally measure the Doppler effect from shifts in the wavelength of spectral lines because it's more reliable, because it's hard to find a continuous spectra and know exactly what it would be like at rest, because there's no star that's at rest relative to us, right? Everything is moving. So the amount of blue shift or red shift tells us an object's speed towards or away from us. It can exactly tell the speed, right down to meters per second, with incredible precision. But there is a limitation. The Doppler shift tells us only about the part of an object's motion towards or away from us. So if an object is moving exactly, parallel to us, it's just moving to the side, so left and right motion, if no towards or away motion, then there is no measured shift, even though the object could be moving at high speed. So we actually know nothing about its speed. And if an object is moving, directly away from us, then we can get a full measurement of its speed. Okay, so that's a great case. But many times, the object is somewhere in between. It's neither moving, directly left and right with no forward or away motion, nor is it a perfect case, like in case number 1. It's like case number 3. And there we have to see if we can have a range of estimates or have some idea of what exactly is its velocity. But that would require some independent measurement. So here's a thought question for you, the 12th of the chapter. I measure a line in the lab at 500.7 nanometers, a spectral line. The same line in a star has a wavelength of 502.8 nanometers. What can I say about this star? All right, so this is the fundamentals. Do you understand the terms and the changes in wavelengths for motion? Way, towards, all right? Or are they just unusually long? Of course, it's a way because the light was redshifted to longer wavelength. All right. Now, the last thing that the Doppler effect can tell us isn't just about the movement of a star away or towards us, but the actual rotation of a star. Because if you observe a star, and so here you are as an observer, well, one side of the star that's rotating is moving towards you. So one edge essentially, right, is coming around, moving towards you. The other edge of the star is rotating away from you. So if you look at the edges and you look at the light on the surfaces of the star, you actually see that effect of red shifting and blue shifting, even if it's not that fast, although the actual rotational speeds of stars tend to be quite fast. So in other words, the light on one side of the star is redder. The true color is right in the middle, right, where there is no relative motion, away or towards, that is. And then the light that is on the other side is blue shifted because that's the light that's moving towards you. So what we see then is we have what would be a continuous spectra of a star at rest, which we can calculate and have a good estimate of. And then we can see that if the star is moving very quickly, that intensity curve gets spread out, smeared out, because the blues become bluer and the reds become redder. So a stretched out continuous spectra from a star tells us that the star is rotating very quickly, and it can be used as just a constant measurement and one piece of data point that's added to every star, its rotational rate. So it's just readily measured for each star. So different Doppler shifts from different sides of rotating objects spread out as spectral lines, right? And they're widest for the fastest spinning objects. So what have we learned in this incredible section? We've learned the 3 basic types of spectra: continuous spectra, emission line spectra, and absorption line spectra. All right? Or one of each, it's a spectrum if it's singular. We've also answered the question, how does light tell us what things are made of? Well, we've learned about how each atom has a unique fingerprint. We've really stressed that point. And we've also learned that we can determine which atoms something is made of by looking for their fingerprint in the spectrum. Those would be either emission or absorption. We've also answered the question, how does light tell us the temperature of planets and stars? Because we know that there's a direct mathematical relationship between continuous spectra and temperature, okay? And we also know that the thermal spectrum is bigger and has a total more amount of energy for hotter objects, all right? And we also answer the question, how does light tell us the speed of distant objects? It's all about the Doppler shift, the shifting of wavelength measured as a blue shift or a red shift. Well, thank you so much for watching this lecture. I hope this entire chapter has been interesting and informative.